The order of the talks has changed slightly, and so they're written here on the board for those who want to read them. And the first speaker is going to be Harry Desmond, and he's going to tell us about the Tully-Fisher and mass-size relations from halo abundance matching.
Thank you. Yeah, so I'm going to talk about a project I've recently finished with Risa Wexler at Stanford.
I think you need to turn. Can you check and see?
Can you hear me? Yeah, it's working.
Oh, okay.
Yeah, it's on. Do you want me to move it up?
Yeah, raise it up then. Yeah.
All right. Is that better? Okay, good. So the basic idea is to see to what extent galaxy formation models based on halo abundance matching are able to account for two important relations of spiral galaxies, and then use the models to extract as much information as possible from the data. So I'll start with a brief introduction to what these relations are. Then I'll describe the modeling approach that I take, and finally I'll show you what this kind of analysis lets us learn and the conclusions that I drew. And I've just put out a paper on this work, so please take a look at that if you'd like more detail. So first, a quick refresher on the Tully-Fisher relation. So this relates galaxy mass, or luminosity, to rotation velocity. Now, in the context of lambda CDM, rotation velocity is determined almost entirely by the dark matter halo, while the other variable in the Tully-Fisher relation is purely baryonic, making the relation a fundamental manifestation of the connection between visible and dark matter on the galaxy scale. It's particularly constraining for galaxy formation models because it has a very small intrinsic scatter, and it's also a good power law over a wide range of mass. The question I'm interested in is how exactly does this relation and the relation between stellar mass and disk scale length arise from the dynamics of dark matter halos, and what do they tell us about the galaxy halo connection? So to get a handle on this, I built a general framework to go from the output of n-body simulations to mock Tully-Fisher and mass-size relations, and then constrained the model parameters by comparing to the data. So here's how the model works. I start with halo abundance matching, which is a simple way of assigning a galaxy's stellar mass to each halo in a simulation by assuming a nearly monotonic relationship between stellar mass and halo mass or velocity. I then assume that each galaxy is an exponential disk with specific angular momentum proportional to that of its halo. Then I can calculate the size of each model galaxy as a function of halo mass, spin, and concentration. That gives me the full rotation curve, the full density profile of the baryonic and dark matter, from which one can calculate the rotation curve and hence the position of each model galaxy on the Tully-Fisher and mass-size planes. So specifically, I'll be using the rotation velocity at the radius enclosing 80% of the I-band light as the dependent variable of the Tully-Fisher relation, and stellar mass as the independent variable, and comparing to the data set of Pisagno et al. 2007. So here are the three parameters in this framework. So the first is the halo property that you do the abundance matching to, and the second is the scatter between stellar mass and that halo property. The third is the ratio between the specific angular momentum of a galaxy and its dark matter halo, which I'm going to assume to be universal. The fourth parameter, nu, describes the impact of disk formation on the halo density profile. So the simplest expectation is that dark matter is drawn adiabatically towards the center as baryons collapse. That would be given in my parameterization by nu equals +1. But it's also possible that supernovae and stellar feedback can transfer energy to the halo and cause it to expand instead, which would correspond to nu less than 0. So I'm going to remain agnostic about those various possibilities a priori and just let the data constrain this parameter. The final parameter controls the impact of selection effects in the model. Now, the Tully-Fisher relation is defined only for spiral galaxies, whilst the halos in simulations host all different types of galaxy. So when comparing theory to data, one should use only those halos from the simulations that would be expected to host spiral galaxies. Now, we don't know exactly which those are, but we can make a reasonable model. So my basic assumption is that rotation-dominated galaxies that would be selected for Tully-Fisher relation studies are likely to have lower than average rotation velocity at fixed stellar mass. There are two reasons why this is sensible. Firstly, there's some evidence from weak lensing and satellite kinematic studies that spirals tend to live in lower mass halos than ellipticals. And second, as I'll show in a moment, this kind of correlation is actually required in order to get a good fit to the Tully-Fisher relation. Okay, so now the plan is to scan through this parameter space and see in each case how well the predicted Tully-Fisher and mass size relations agree with the observations. By writing down a likelihood function based on the difference between power law fits to the predicted and observed relations, I can then use an CMC algorithm to find the posterior distributions of these model parameters. And here they are for a particular abundance matching model. Two most important points. One, to get the normalization of the Tully-Fisher relation right, you need halo expansion. So nu less than 0 is excluded, and pure NFW profiles won't do. And you also need the specific angular momentum of each galaxy to be similar to that of its host halo, in agreement with Reinhard's results from earlier this morning. So that would be J near 1. Secondly, to get the scatter in the Tully-Fisher relation small enough, you need low scatter in the abundance matching step, and you also need a fairly strong selection bias towards slowly rotating galaxies. If you satisfy both of those requirements, you can get a good fit to both the Tully-Fisher and mass size relations in this framework, except for the scatter in sizes. So this plot on the right shows the distribution of scatter values of lots of mock data sets drawn from the best fitting model compared to the value in the real data, which is this red line. So as you can see, the model always predicts too high a scatter. And the reason for this is very generic and easy to see. The assumption that galaxy and halo specific angular momentum are proportional means that galaxy size is proportional to halo spin. But we know from simulations that spin has a scatter of around 0.25 dex at fixed mass, which is already larger than the observed scatter in sizes at fixed mass. And there's extra scatter under this assumption from variations in halo concentration. So galaxy sizes aren't quite as simple as angular momentum partition with the dark matter. Another interesting thing I studied is the correlation between the residuals of the Tully-Fisher and mass size relations. So for any galaxy, take the difference between its rotation velocity and the velocity expected for a galaxy of that mass from the power law fit to the Tully-Fisher relation. That's the velocity residual. Then do the same thing with radius to get the radius residual and plot the two against each other. If there's a correlation, then galaxies with the same mass but different size are systematically offset in velocity. Now this relation is interesting because one might expect there to be an anti-correlation. Smaller than average galaxies at fixed stellar mass should rotate faster than average simply because they're more concentrated. This plot shows the prediction from the model with parameter values chosen to fit the Tully-Fisher relation best. But if you look at this in the real data, there's absolutely no correlation at all. Rotation rate is entirely independent of size at fixed mass. And as you can see, there's some discrepancy. And that can be quantified statistically using the Spearman's rank correlation coefficient. So very quickly, these histograms show the distribution of Spearman's rank correlation coefficient values of lots of mock data sets drawn from the model compared to the value in the real data. Value of 0 corresponds to no correlation. These different histograms are just different sets of parameter values within my framework. Bottom line is that within this framework, the data are not consistent with having been drawn from the theoretical galaxy population for any values of these free parameters. So here's what I think the data is telling us. As I said, we predict an anti-correlation because smaller than average galaxies at fixed stellar mass have rotation curves that peak at higher values. So what we need is for smaller galaxies to live in halos that are less massive or less concentrated, so that the increase in the baryonic rotation curve is offset by a decrease in the dark matter rotation curve. And as to how or why it should come about, I'm not sure. There are some ways I can think of modeling it theoretically. One way would be to correlate the scatter in the abundance matching with halo spin, for example. Another way might be to use to drop the assumption of angular momentum partition between the dark and visible matter and use a conditional abundance matching to set the size of the stellar disks. But in either case, more work needs to be done to create a simple framework to predict galaxy sizes from basic properties of halos. And I'll end there. Thank you.
Thank you, Harry. We have time for a quick question. Anybody?
Nobody else? Yes. Your assumption about the angular momentum tied to the halo may not apply to the central regions if there's in fact feedback, which then redistributes that angular momentum in a different way. Would that naturally explain the current discrepancies or not? Do you know?
I don't think it naturally would. It might be possible to build some kind of model where an effect like that could help. As this model stands, it's simply a single number for the angular momentum of the galaxy, and then if you assume an exponential disk, then that sets the entire distribution. Certainly, yes. Yeah, there could be coupling with feedback as well. Yep. But that's all beyond the scope of this most simple type of parameterization.
Can the next speaker come and prepare?
So you're mentioning the need for halo expansion. Can you give us some quantitative estimate of by how much you need to expand?
Yeah, good question. So it depends to some extent on the details of the abundance matching. So for simplicity and for the sake of time, I only showed you the results for a single abundance matching model. So this is when you match to V peak, which is the maximum rotation velocity of the halo at the time when that quantity is maximum over the mass accretion history of the thing. So in that case, the plot I showed earlier, you can see that mu equals 0, which is no expansion or contraction, is sort of 3 sigma discrepant. If you use an abundance matching model based, for example, on halo mass, so you match between stellar mass and the present-day virial mass of a halo, you can actually have a small amount of contraction. You don't need significant halo expansion. So the effect is not necessarily significant. What is significant is that standard adiabatic contraction is clearly ruled out for all of these models.
Just a quick comment. I'm here.
Oh, yeah.
Hi. So this is great work, and it's very similar to, the results at least are very similar to what we did in Aaron Dutton in 2007. Mm-hmm. And again, the constraint that you get from the residual correlation is a very strong one. And you pointed out that one way to do it is to have the scatter in the halo mass stellar mass relation be correlated with the spin parameter,
yep,
or the scatter in the spin parameter. And in Aaron's paper, we pointed out that one sort of natural way in which that might come about is if you have a star formation threshold density. So then if you have a large spin parameter, then the gas is very spread out and you're less likely to have a lot of star formation. So you make less massive galaxies and galaxies and halos with a larger spin parameter. And that sort of was included in our model, and that really made a big difference.
Right, certainly that could be one way of doing it. I'm slightly concerned about that particular way of doing it. That would, as you say, reduce the anti-correlation of the residuals for the stellar mass Tully-Fisher relation. But if you looked at the baryonic mass Tully-Fisher relation, I believe that would not decrease the magnitude of the predicted anti-correlation. And I also think there are some results that suggest that those two are not correlated. But that's sort of beyond the scope of this basic abundance matching type business.
Okay, we got to move on. Right. The order of the talks has changed slightly, and so they're written here on the board for those who want to read them. And the first speaker is going to be Harry Desmond, and he's going to tell us about the Tully-Fisher and mass-size relations from
to extract as much information as possible from the data. So I'll start with a brief introduction to what these relations are. Then I'll describe the modeling approach that I take. And finally, I'll show you what this kind of analysis lets us learn and the conclusions that I drew. And I've just put out a paper on this work, so please take a look at that if you'd like more detail. So first, a quick refresher on the Tully-Fisher relation. So this relates galaxy mass, or luminosity, to rotation velocity. Now, in the context of lambda CDM, rotation velocity is determined almost entirely. All right, is that better? Okay, good. So the basic idea is to see to what extent galaxy formation models based on halo abundance matching are able to account for two important relations of spiral galaxies, and then use the model.
halo abundance matching.
Thank you. Yeah, so I'm going to talk about a project I've recently finished with Risa Wexler at Stanford.
I think you need to turn. Can you check and see?
Can you hear me? Yeah, it's working.
Oh, okay.
Yeah, it's on. Do you want me to move it up?
Yeah, raise it up.